Hello, welcome back to my channel. So we are now going to start reviewing, going over everything for the spring semester exam. So this is basically all of it, the entire semester. So I'm going to do different parts of each unit, so that way we have time to cover every single topic the best to my ability. So part 1 will be covering unit 7, which is covalent bonding. So that covers the properties of covalent bonding, covalent naming, Lewis structures, VSEPR theory, polarity, and IMFs. So, and this is basically like the table of contents. I'm going to start here with a fresh sheet of paper. And first thing we're going to talk about is covalent properties. So, how do we know something is covalent, like a compound is covalent? We got to remember that covalent compounds are between two nonmetals. So, it's nonmetal plus nonmetal. So, can you think of an example of a covalent compound? For example, it can be CH4, or it can be NF3. So notice how these elements, they are both nonmetals bonded together, so they are covalent compounds. So remember, nonmetals are all from this side, right side of the staircase, so like CH4, NF3. Again, hydrogen is a nonmetal, so that is included that side. So that is a property of covalence. They are nonmetals. The next thing you need to remember is that they share electrons. Since nonmetals are anions, anions love to gain electrons. So since nonmetals, they both love electrons, they like to share. They're like holding hands. Okay? And then they have low melting points. So melting, boiling points. So kind of the same thing. So they have a low temperature to melt or to boil. So if you think about sugar, sugar is a compound that consists of carbon, hydrogen, and oxygen. So if you think about melting sugar, it doesn't take very long. So that's why it has a low melting point, which is why it melts pretty quickly. Okay, so low melting and boiling point, and they're also liquid and gas, depending on the compound, at room temperature. They're not solid at room temperature. So little hint, hint, wink, wink, nudge, nudge. You got to remember the sharing the electrons and what it consists of, nonmetals, right? So those are covalent properties, pretty straightforward. The next thing I'm going to cover is covalent naming. How to name covalent compounds. So we've done the charges and the crisscross a lot, but with covalent naming, we use something called prefixes, and you have to know your prefixes. I'm not going to give that to you. So your prefixes is from 1 through 10. 1 is mono, 2 is di, 3 is tri, think of triangle. I'll zoom in, perfect. 4 is tetra. If you know the game Tetris, Tetris is just different shapes with 4 squares. That's where tetra came from. 5 is penta, like pentagon. 6 is hexa. 7 is hepta. 8 is octa, like octagon. 9 is nona. 10 is deca, like decade, 10 years. Okay, so I do want to mention very easy to mix up, and don't fall for it on the exam. The 6 versus 7, hexa and hepta, they look very similar. Don't mix up between the two. So think of hexagon has 6 sides, so hexa is 6, hepta is 7. Okay? And 5 also. I've seen a lot of mistakes in the past too. Penta is 5, penta is not 6. Okay? So 5, 6, and 7, you gotta make sure that you get those right. Okay? So those are the prefixes. And you gotta remember the main rule with mono, the one prefix that's only used on the second nonmetal. So I'm just gonna put this note here. No mono on the first nonmetal. So the di, tri, tetra, etc., that can be in the first nonmetal, but mono is only for the second nonmetal. So for example, let's say I give you NO3. So N, there's only one nitrogen, so you just do nitrogen. And then you have 3 O's, so 3 oxygens. So the prefix for 3 is tri. So instead of tri-oxygen, again, the ending is always "ide." So instead of oxygen, trioxide. Okay? Next example, let's say I give you I4 and 5. So you have iodine and the prefix is 4. So tetra, iodine, and then N5, so 5 is penta, penta, and then nitrogen is nitride. Alright, let's do the other way around. When I give you the name, let's say I give you hexa, nitrogen, pentasulfide. Let's do that. All you gotta do is first figure out your symbols, nitrogen, sulfide, and then do your subscripts based upon your prefixes. So nitrogen is N, sulfide is sulfur, so S, and then you look at your prefixes. So hexa is 6, so N6, penta is 5, S5. So the nice thing about covalent naming is that there's no crisscrossing, switching nonsense. It's just you do it as you see it. Okay? Let's do one more. Since I did 2 of this, I'm going to do 2 of the other way around. Let's say I give you octaphosphorus dichloride. Okay? Try to do this by yourself. I'll give you a few seconds. Alright, so phosphorus is P, chloride is Cl, and then you look at your prefixes. Octa is 8, di is 2. So that's how you do your formulas. Alright, so that is your covalent naming. Alright, next on the list is, I believe, Lewis structures. Alright, Lewis structures. This is where you have to know, like, your central atom, how to draw your bonds, etc. Alright, so just remember that your central atom is always usually the first element listed in your compound, but it's usually always the least electronegative atom. That is your central atom. Now, what does that mean? I'm going to grab my periodic table. So again, electronegativity is more to the left, electronegativity decreases to the left. So basically the element more to the left will be your central atom. So, and also carbon, we love carbon. Carbon is a very special element. It is always the central atom, no matter what. And then you'll always have to count your valence electrons first. And how do you know how many valence electrons something has? You use your periodic table, of course. And we've done charges a lot recently, and we haven't done valence electrons in a bit. So just as a reminder, let me zoom out a little bit. Your group number, your column number tells you how many valence electrons. So group 1 is 1 valence electron. Group 2 is 2 valence electrons. Again, we skip the transition metals. That's a whole other story. Group 3 is 3 valence electrons. Group 4, 4 valence electrons. 5, 6, 7, 8. The max an atom can hold is 8 valence electrons. So, column number or group number equals number of valence electrons. Okay? So let's do an example. Let's do something really simple, CH4. Okay, so as we can see here, carbon is the central atom, and then we draw 4 H's surrounding it. So we're doing the skeletal, the structure. Okay, and now we count the number of valence electrons that this total compound has. All right, so carbon is in group 4, so 4 valence electrons, and then carbon has 4, and then hydrogen has 1 valence electron, and there's 4 of them. 4 hydrogens, 1 of each, so 4 plus 4, we have a total of 8 valence electrons to work with. Okay, and then we add our bonds. Remember, 1 bond equals 2 electrons. And then we have lone pairs, which we'll probably add in a second in our next example, also is 2 electrons. So we always assign electrons in pairs. So let's do bonds first. So we're just connecting them. And each, if it helps, you can do your dots like that just so you can visually see these elements are sharing electrons. Okay, I just did 4 bonds, and each bond is 2. So 4 times 2 is 8. I have used all of my electrons. This is the complete structure of CH4. Okay, let's do another one. Let's try to do PCl3. Alright, so let's do our little structure here. P in the middle, and then Cl, Cl, Cl. And then we count our electrons. So P is in group 5, so 5 electrons. And then Cl is in group 7, has 7 valence electrons times 3. 3 of them, that's 21. 21 plus 5, we have a total of 26 electrons to work with. Right, next we add our bonds. We have 3 bonds, so 3, so 2, 4, 6. We just use 6 electrons. We have 20 electrons left. From there, after we do the bonds, now we start from the outside and then we work our way in. So, again, I'm going to do the dots here so you can visually see what's going on. Okay, now, as you can see here, the reason why I did these dots, just so you can visually see, like, okay, I have 1 electron to the phosphorus, 1 electron to the chlorine, 1 electron to the phosphorus, 1 electron to the chlorine, so on and so forth. So you can see here that each chlorine right now on the outside has 1 electron, but it's in group 7. It wants 7 electrons. So since it has 1 so far, I need to add 6 more for it to be happy. Okay? So this is where I come in and add 6 more electrons. And again, I'm assigning it in pairs. So 2, 4, 6. Okay? Same thing here. 2, 4, 6. 2, 4, 6. Okay? I just used 6 electrons for each of these, so each chlorine now has 7 total. So 6 times 3, I just used 18. I have 2 left. So when I have leftover electrons like that, I just add it to the middle, which works out because here, if you look at phosphorus, there's 3 so far. 1, 2, 3. It's in group 5, so it needs 2 more for it to be 5. So doesn't matter where you put it as long as you put in pairs like that. That is the Lewis structure for PCl3. Alright. Let's do one more example, and I'm going to have you try this by yourself. And it's a well-known one. H2O. I'm going to have you try this, pause the video, and then play once you got it and to check your work. Alright, this is the structure for H2O. Now, remember H is actually, I should have added it to my rules here. H is always on the outside because here's the thing, hydrogen only has 1 electron, so it can't be in the middle because otherwise it will have more than 1 electron. So that's why we always put hydrogen on the outside. I've said this all the time, hydrogen is special, it breaks all the rules, and this is one of the rules broken. So even though hydrogen, it's less electronegative than oxygen, it is still on the outside just because it can only handle 1 electron. Then oxygen, if you can see here, let me just color here. So hydrogen has 1 electron, 2 of them, so that's 2. Oxygen has 6 valence electrons, so total I have 8. When I added these bonds here, 1, 2, I just used 4 electrons. So I have 4 left. And since hydrogen is already happy, I'm going to put those 4 electrons in the middle. So that is how you draw a Lewis structure. So I hope it's coming back. Now the next part of our list here for covalent is Vesper theory. So Vesper is, we're going to use Lewis structure, is a huge part of it. So I'm going to flip over to the back. Alright, Vesper theory. Remember, Vesper theory is like the geometric shape of like Lewis structures. So there is the electron geometry versus molecular geometry. And you get to use this formula sheet, not formula sheet, like reference sheet. So it's your responsibility to know the difference and how to like use it. So it all depends on your Lewis structure. So the electron geometry tells you the number of regions. So I like to call it the number of things around the central atom. It's always related, so like with this, it's always related to the central atom only, so not the entire structure itself. So number of regions around central atom. And then molecular geometry is more specific. So number of bonds versus lone pairs around central atom. Again, it's all the central atom. Alright, so I'm going to just jump right into the example, show you again as a refresher on how to read this reference sheet. So for example, again, I'm just going to do CH4 again. I think I'm just going to do the same examples as what we just did. So CH4, again, we just did the Lewis structure. Just going to repeat that. Okay, so when we look at our electron geometry, so I'm going to just abbreviate it as EG versus MG, so electron versus molecular. So we're going to see how many domains, how many regions around the C. So we have 1, 2, 3, 4. We have 4 domains, 4 regions. And then when we look at our bonds versus lone pairs, again around the C, so I have 4 bonds, 0 lone pairs. Okay, so when we look at our electron geometry, again, we're going to look at our chart here, and we have 4 domains. Number of domains, we have 4, so our electron domain geometry is tetrahedral. Okay, so that is our electron geometry. Remember, tetra means 4, hence the 4 bonds. Okay, molecular geometry, we have 4 bonds and nothing else. So when we look at our tetrahedral, you can see here, okay, how many lone pairs does carbon have? It has 0, therefore it is still tetrahedral. So that's the rule here for VSEPR. If there's no lone pairs, the molecular geometry is the same as electron geometry. So molecular geometry, it is still tetrahedral. Alright. So that is the difference, and it's just about having the correct Lewis structure and figuring out how to read the chart correctly. So let's do the next example, which I think we did. What was the next example? PCl3. And then our Lewis structure looks something like this. Alright, so electron geometry. We have, again, how many things, how many regions around the P? 1, 2, 3, 4. Again, doesn't matter bonds or dots, it's still a domain. 1, 2, 3, 4. Molecular geometry, that's when you distinguish between bonds and the lone pairs. We have 1, 2, 3 bonds and 1 lone pair. 1 lone pair. Okay, so our electron geometry, so 4, again, we just discussed it, tetrahedral. But this time we have 1 lone pair. So when we look at our chart, we have tetrahedral, and then we have 1 lone pair. That will be trigonal pyramidal. So you got to be careful, especially with multiple choice. If I ask you, you know, what is the molecular geometry, you got to make sure you choose trigonal pyramidal. Tetrahedral can be an option, but since I'm asking for molecular, it has to be this one. So you got to be careful. Okay, let me give you one last one. Let me give you H2O now. Try this by yourself. Figure out your electron geometry and your molecular geometry. Pause the video. Alright, so you should have gotten electron geometry as tetrahedral because there's 1, 2, 3, 4 regions, and then it is bent because it has 2 lone pairs Right here, bends. Perfect. So I hope it makes better sense with how to read the VSEPR chart. Again, it all depends on your Lewis structure, but that's pretty much VSEPR theory. Next thing on our list is IMFs, intermolecular forces. Just as a reminder, stands for intermolecular forces. Alright, and we have 3 types. We have London dispersion forces, or LDF. So with LDF, this is in all molecules. And nonpolar molecules only. So what I mean by that actually is that and I'll talk about polarity in a second, but if a compound, if a molecule is nonpolar, it is LDF only. And again, hopefully it'll make better sense once I tell you all the IMFs. So that's the first one, London dispersion. The next one is called dipole-dipole. I call it dipole-dipole. DD. So this is with polar molecules only. Okay? Then last but not least, we have hydrogen bonding. HB. Okay, so this is also polar, but what makes it special, obviously there's hydrogen, but it has to bond with 3 specific elements: nitrogen, oxygen, or fluorine. So we all say hydrogen bonding is ENOF. So NOF, that makes a hydrogen bonding. If it's H with Cl, that's not hydrogen bonding. If it's H with C, that's not hydrogen bonding. Only these 3 make it hydrogen bonding. Alright? And it has to be H with these. Not only nitrogen or not only oxygen. Obviously there has to be hydrogen bonded to it. Okay? So while we're at it, we're going to talk about polarity. I actually should have started with that first, but that's okay. Polarity. So we have polar, and again, it all relates to Lewis structures. So polar means it's asymmetrical. It's an uneven distribution of electrons. Then nonpolar is symmetrical. And I know it's weird because you may think, oh, nonpolar, non-symmetrical. No, it's the other way around. It is what it is. And nonpolar is uneven it is an even distribution of electrons, where polar it is not. Okay, so if we actually can look back on these structures here, since I've already drawn them, as you can see here, CH4, it looks pretty symmetrical. It's an uneven, or it is an even distribution of electrons, so it is non-polar. Okay, and then we have PCl3. It may look symmetrical, but the trick is if there are dots in the center, if there are lone pairs in the center, it is polar automatically. Okay, however, the only two shapes that are nonpolar is square planar and linear. So these two, they're the only ones that are nonpolar, whereas everything else that have dots in the center are polar. Okay? So I'm going to do the same examples as up here. So CH4, I'm not going to redraw the structures, but CH4, we already talked about it, is nonpolar. So since it is nonpolar, it is automatically just LDF, just London. It is nothing else because it is not polar and it is not hydrogen bonding. So CH4, even though there's hydrogen, carbon is not one of these three elements. So it is only LDF. Alright, PCl3. We just looked at it. There's dots in the center. It is polar. Therefore, and there's no hydrogen or anything, so it's just dipple-dipple. And then we have H2O. H2O is polar, and since hydrogen is in it bonded with oxygen, part of the NOF, it is hydrogen bonding. But also remember that if a molecule has, so another thing you need to remember is that LDF is the weakest forced, while hydrogen bonding is the strongest. So if a compound has a higher IMF, then it also has the lower one. So for example, if like CH4 is LDF, it is LDF only, okay? And PCl3, it is dipple-dipple, but it also is LDF because, again, it is in all molecules. And then if a compound like H2O has hydrogen bonding, it is also dipple-dipple and it is also LDF. So like if it's higher up in the strength, then it also has the lower one. So hydrogen bonding, dipple-dipple, and LDF. So I hope you can see the pattern there. Alright, so I'll give you two more examples, and I'm going to have you try this by yourself. You're going to draw the structure, you're going to figure out the polarity, and then all the IMFs possible. So let me give you two. Let's say I give you an H3, and then I'm going to give you, I'm blanking out. Let's see. PBr5. Let's try that. Alright, so again, pause the video, do the structure, figure out the polarity and the IMF. So it's going to take a few minutes, and once you got it, play the video and see if you got it right. Okay, so NH3. This is the structure. Got 3 bonds and got a lone pair here to satisfy the nitrogen. It is polar because there are dots in the center, and since it's hydrogen bonded with nitrogen, one of these 3 elements, it is automatically hydrogen bonding, automatically making the rest of them possible. Dipple-dipple and LDF. Now PBr5, this is the structure. As you can see here, it's pretty symmetrical, looks like a nice star. It is nonpolar, therefore it is LDF only. Alright, so that is pretty much all of covalent bonding. This is all of Unit 7. So I hope this helps. Let me know if you have any questions, and like, comment, subscribe.